Hello and welcome to ElectroPHY channel. In this video we are going to talk about Faraday's law of induction. According to Faraday's law, if a magnetic field changes by the time, it induces a voltage in the loop wire near it, which is called back EMF. Mathematically, Faraday's law is described with this formula. N is number of loops and phi is magnetic flux. The minus sign in this formula is Lenz's law, which means that the direction of the current induced due to the Faraday's law is such that the magnetic field created by it opposes the changing of the magnetic field of the source. You can distinguish the direction of the induced magnetic field with the right-hand rule as it is shown in this picture. Now we want to experiment Faraday's law. First experiment is turning on LEDs with coil. We want to see Faraday and Lenz's law at the same time. In these pictures you can see LEDs glowing, that is due to exiting or entering a coil through a magnetic circuit. Our setup has magnets and ferrite sheets. In other words, we have a magnetic circuit, which is very similar to a transformer core. A proper coil can go through this ferrite from top. The magnetic field streamlines are shown in the picture. The magnetic reluctance of ferrite sheets is lower than the air gap. In other words, the magnetic field closes its path inside the ferrite sheet easier than the air. The reluctance in the magnetic circuit is analogous to resistance in electrical circuits. This setup makes a constant magnetic field. We use a coil to drop in the ferrite sheet's holes from the top as said before. The coil is connected to two LEDs that are back to back with series resistors. The schematic of the circuit is shown in the right side. Each LED is turned on in one direction and we can check Lenz's law with this structure. If you don't know about LEDs, it's a diode and let the current go in one direction and emits light. Here you can see the two LEDs that are connected to the coil in parallel and reverse. Here you will see while entering the coil, the left LED will turn on. And here, while exiting the coil, the right LED will turn on. Now second experiment, slow falling coil. In this experiment, we will drop a short circuit and an open circuit coil in previous ferrite structure. In these pictures, you can see the coil in short circuit and open circuit states. The schematic of the open circuit coil is on the right side. In this case, we have induced voltages, but current can't flow in the circuit because current requires a closed loop. The open circuit coil drops with a normal speed and it won't make any magnetic field. The schematic of the short circuit coil is on the right side. In this case, we have induced voltage as well as the induced current. The induced current makes a magnetic field that opposes the main field and slows down the falling speed of the coil. In the case of short circuit coil, you can see that because of Lenz's law, the induced magnetic field is in the opposite direction of magnetic field of source or magnets. Here you'll see the experiment of open circuit coil. The coil is expected to fall down with normal speed. Now let's short circuit the coil. As you can see, the coil is dropping with a slower speed. Now the third experiment, dropping magnet inside a metal pipe. What will happen if you drop a magnet through a metal pipe rather than a simple object like battery? While the magnet is dropping, the magnetic field changes and it induces a voltage in the metal pipe. The induced voltage causes the current in the pipe. Due to the Lenz's law, induced current opposes the main magnetic field. Therefore, magnetic fields repel each other and it slows down the speed of magnet like the previous experiment. These green lines are magnetic field of magnet and these are magnetic fields of induced current. In this experiment, the battery is used to show the speed difference of falling and doesn't do anything else. While dropping battery, because there is no magnetic field change, no current is induced and therefore it falls with normal speed. Here first you'll see the magnet dropping through the pipe. Pay attention to the speed of falling. And here you'll see the battery as a non-magnetic object dropping through the pipe. Here you'll see the dropping of magnet inside the pipe from top view. Here you'll see another experiment in dropping magnet with longer metal pipe. You saw that it takes too long for the magnet to reach the end of the pipe. Special thanks to Professor Mohseni, great master of Tehran University, because he helps and lets us record these videos. Thanks for watching. Hope you learned good things. If you like this video, hit the like button and subscribe to support our channel and get more like this video.